Paper 2, 2018, question 1. So I've got some experiments with some different concentrations of hydrogen peroxide, which is breaking down to make water and oxygen, and measuring the volume of water in each to start off with, the temperature and the catalyst. So the temperature is staying the same, the amount of water in the mixture is staying the same, so concentration and temperature is staying the same. But the sort of form of the catalyst, whether it be lumps or powders, changing, and the concentrations of the initial hydrogen peroxide are changing. So let's have a little look. Explain in general terms how a catalyst increases the rate of the reaction. It provides an alternate route to the reaction, and in doing so lowers the activation energy. Label a line on each experiment number. So what have I got here? I've got the initial one for experiment number 1. In experiment number 2, everything stayed the same, so concentrations stayed the same except when you're using a powdered catalyst. That will mean that the reaction will go faster, but the amount of products, because the amount of reactants is the same, will be exactly the same as well. So it's going to reach that line, but it's going to reach that line quicker. So it'll go up steeper, but end up at the same amount of volume of oxygen produced because the amounts of reactants are the same. So that's for experiment number 2. Experiment number 3 is going to go at the same speed as experiment number 1. So it's going to reach the maximum amount of product at the same time here, but it'll go more shallowly because it'll produce more slowly because you've got lumps of catalyst and you've got a lower surface area. Explain in terms of the collision theory. Increasing the concentration of hydrogen peroxide, the particles are closer together, so you'd have more successful collisions, more frequent successful collisions. Successful collisions would happen more frequently because the particles are closer together. So let's have a look at question 2. We've got citric acid in fruits. Student analysed the citric acid to determine its purity. Student dissolved a number of milligrams, 784 milligrams of citric acid in water. Prepare 250 centimeters cubed of solution in a volumetric flask. Titrate 25 centimeter samples of this. Right, okay, so that's important. So the amount of citric acid that they've actually only taken a sample, 25 centimeter cubed out of the 250. So they've taken a tenth of the amount of the citric acid in a sample. Titrated it with 0.5 mole per decimeter cubed. So we've got the concentration of sodium hydroxide using phenolphthalein as an indicator. Okay, we've got the equation here, so that might be important. 1 mole of the acid reacts with 3 moles of the sodium hydroxide. Student rinse the burette before filling it with the sodium hydroxide solution. Why the student should use sodium hydroxide to rinse the burette? Well, sodium hydroxide is going to go in the burette, so use sodium hydroxide to rinse it, otherwise the water may dilute the sodium hydroxide that's going to be in there. Student carried out several titrations. Complete it. So what you do is you take the final, take away the start, and you put it there. Final, take away the start, final, take away the start, final, take away the start, and you put them underneath. And you make sure they're all to 4 significant figures. All of these look as if they're to 4 significant figures. The first one is rough, so that needn't be. That's not actually to 4 significant figures at all, but the others looks as if they're starting out at least to 4 significant figures. I'm going to put them to 4 significant figures: 24.00, 23.70, 23.90, and 25.2 is just my rough one. What is meant by concordant results? Concordant results means that the results are no more than 0.1 apart from each other. So calculate the mean using 2 concordant results. Any 2 that are no more than 0.1 apart from each other. So that's 1 and 3. Titer 1 and titer 3 are 0.1 apart. So I'm going to use titer 1 and titer 3 and ignore the others that are further apart than 0.1 from these 2. And so they're not concordant. So 1 and 3 are concordant. Use of titrations 1 and 3. Let's take an average: 23.90, 24.00. Add them together, divide by 2, 23.95. The total uncertainty when using the burette is 0.15. So even though the burette's had 2 readings taken from it, the total uncertainty, that means that they've taken into account the fact that you've had 2 readings off the burette, is a combination of uncertainties, the start reading, the final reading, the determination of the endpoint. So everything's been taken into account. Use this to calculate the percentage uncertainty for the use of the burette. So you've got 0.15 is how far out it could be. You're using 23.95 centimeters cubed, so you divide the smaller by 0.15 divided by 23.95 and multiply by 100%. 0.63%. Use your answer to question 0.23 to find the mass in milligrams of citric acid dissolved in 25 centimeters cubed. The relative molecular mass of citric acid is 192. So, what have I got? I've got, use the answer in question 2.3. So, I've got a volume of sodium hydroxide. I've got a concentration of sodium hydroxide, 0.05, and I've got a volume. That needs to be in decimeter cubed, so divide by 1000 to turn centimeter cubed into decimeter cubed, 0.0295 decimeter cubed, and I've got 0.05 concentration. So moles, concentration equals moles divided by volume, moles equals concentration multiplied by volume. Well, there's my concentration, there's my volume in decimeter cubed, 23.95 divided by 1000, and that equals, that should say equals there, 0.001187. So my number of moles is 0.001187 moles of sodium hydroxide. If I refer back to my equation, I've got the number of moles of sodium hydroxide, which is this. 1 mole of the acid reacts with 3 moles of sodium hydroxide, 1 to 3. So I take the number of sodium hydroxide, number of moles of sodium hydroxide, and if I divide by 3, it will give me the number of moles of the acid. So if I take that 0.001187 and divide by 3, I'll get the number of moles of acid. I need to multiply by 10, however, because I've worked out the number of moles of acid in 25 centimeter cube sample. I want to know how many are in the 250 centimeter cube sample. 25 centimeter cubes is a tenth of this amount, so I've worked out the number of moles of acid in the 25 centimeter cubed. If I multiply by 10, I'll work out the number of moles of acid in the volumetric flask at the beginning. So now I'll multiply by 10. It's 0.003992. That's the number of moles of acid that are actually in the flask. So what am I trying to find out now? Find the mass in milligrams of citric acid dissolved in there. So I've got moles. Moles equals mass divided by mR. So moles multiplied by mR equals the mass. Moles, mR 192. I think it gives you that in the question. No, it doesn't give you that in the question. You need to work it out. Oh yes, it does, 192 here. It gives you in the question here, 192 of the citric acid. So number of moles multiplied by the mR gives me the number of grams. Now it wants the number of grams, not the number of grams, it wants the number of milligrams. So if I'm turning grams into a smaller unit amount, milligrams, then I multiply by 1,000, 766 milligrams of acid. Calculate the percentage purity of sample of the acid. So this is how much I got. .784 milligrams of impure citric acid were put in there. So I know that 784 milligrams of impure, and I've worked out from my calculations this is the mass of the acid, 766, and 784 is the amount of impure acid. So my percentage purity is the amount of acid in there divided by the amount of acid and impurities, 784, multiplied by 100% equals 97.7%. Question 3. This question is about enthalpy changes. When ethanoic acid reacts with sodium hydroxide, the enthalpy change delta H is minus 56.1 kilojoules per mole. I've been given an equation. Ethanoic acid and sodium hydroxide. Calculate the temperature rise. 25 centimeters cubed of 2 mole per decimeter cubed ethanoic acid. I'm not going to read any further than that. I've got a volume and I've got a concentration. So concentration equals moles divided by volume. So I've got a volume and I've got a concentration. So concentration equals moles divided by volume. Therefore, moles equals concentration multiplied by volume. So moles is concentration multiplied by volume. There's my concentration 2. My volume's in 25 centimeters cubed. It needs to be in decimeter cubed. Centimeter cubed into decimeter cubed, smaller into larger units, so divide by 1,000. And it works out as 25 divided by 1,000, or 0.025 multiplied by 2, will give me the number of moles of ethanoic acid that I have. Okay? It reacts with the same number of moles of aqueous sodium hydroxide, 25 centimeters cubed, 2 moles of that, sodium hydroxide, 1:1 ratio. Okay. Assume that both solutions have the same initial temperature, have a density of this, specific heat capacity. So what have I got? Specific heat capacity, it must mean that I'm using Q equals delta H equals MC delta T. I must be doing that because that's the only one with specific heat capacity C in. So, first of all, what am I going to find out? I need to find Q or delta H for this reaction. Well, it tells me that minus 56.1 kilojoules of energy are released, minus 56, when I have reacted a mole. Except that I haven't reacted a mole, I've only got 0.05 moles. So if 1 mole gives out 56.1 kilojoules of energy, then 0.05 multiplied by 0.05, it'll come out as 2.805 kilojoules, or 2,805 joules, multiplied by 1,000, get into the smaller unit of joules, 2,805 joules of energy for 0.05 moles that I have. So look at what I did again. I worked out the number of moles that I have. This is for 1 mole, multiplied by this smaller number of moles, multiplied the enthalpy change for 1 mole by this smaller amount of moles, and I've worked out the number of kilojoules of energy that are released, and I've put it into joules, because in this equation here, delta H needs to be, or Q needs to be in joules. So 2,805 equals MC delta T. What's the mass of the liquid that I've got? Well, I've got 25 centimeters cubed of each. That's 50 centimeters cubed. Assuming a density of 1 gram for every centimeter cubed, I've got 50 centimeters cubed, or 50 grams. So my mass is 50 grams. C is 4.18, specific heat capacity. Delta T, I don't know. I've multiplied out the 50 by the 4.18, so 2,805 equals 209 multiplied by delta T. Delta T is 2,805 divided by 209, 13.4. Everything here seems to be to 3 significant figures, 4.18, 3 significant figures. I'm going to keep it as 3 significant figures, 13.4. I've plotted some points on the graph here, and I've extrapolated to time 4, because it says that I'm measuring the temperature in a polystyrene cup during this reaction, and on the 4th minute I've got ethanoic acid in a cup, and in the 4th minute I've added some sodium hydrogen carbonate. I can't measure the temperature at the 4th minute, that's why I haven't got a reading, but I've got readings for the others that have been plotted on the curve on the point here. But I need to find out what temperature it is at time 4 by extrapolating forwards and extrapolating backwards. Now this, I ignore that point, because the reason it's not dropped straight down to here and then come back up is because that the thermometer can't respond that quickly. But it will drop down here to about here and then start rising up. I need a line of best fit. Remember, a line of best fit can be a curve. A line of best fit on this, forming a curve and extrapolating back to temperature, to time 4. I think it's going to work out 11.2. There we go. I've plotted it onto the graph now. It comes out at about 11.2. So I've got 17.2 and 11.2. So the temperature change is around about 6.0. So about 6.0. I'm allowed on my mark scheme 0.2 either way out. So I'm allowed 5.8 up to 6.2. We've got two alkanes. It looks as if we've got nonane and 2,4-dimethylheptane, and it's asking us to deduce an expression for the relative state in general terms an alkane, a general formula. Sorry, the general formula from alkane. So it's CnH2n plus 2. So CnH2n2 plus 2. If you want to check that, 1, 2, 3, 4, 5, 6, 7, 8, 9 in nonane, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So you've taken the 9, multiplied by 2 to make 18, and added 2 to get the number of hydrogens, which is 20. So CnH2n plus 2. Deduce an expression for the relative molecular mass of an alkane in terms of N. So in terms of the relative molecular mass then, a carbon has got a mass of 12 and a hydrogen's got a mass of 1. So for every carbon has got a mass of 12, and then you've got N numbers of 12, and hydrogen's got a mass of 1, and for every hydrogen with a mass of 1, you've got 2N plus 2 with a mass of 1. So to work out the relative molecular mass in terms of N, a carbon is a 12, and you've got N numbers of cardinal atoms, so N numbers of 12, mass 12, and 1 times 2N plus 2, a hydrogen is 1, I've got a mass of 1, and you've got 2N plus 2 numbers of hydrogens. Expand those brackets, 12N equals 2N plus 2, 14N plus 2. Explain why non-N has a higher boiling point than 2,4-dimethylheptane. It's because it's a straight chain. The chains can pack closer together. If they pack closer together, there's more and stronger van der Waals forces. So non-N has more and stronger van der Waals forces between the molecules because the non-N molecules can pack closer together because it's a straight chain without branches. Given an equation for the complete combustion of nonane, so we've decided that nonane is C9H20, so C9H20 plus O2, complete combustion, so combustion is reaction with O2, complete combustion means it makes carbon dioxide and water. That means when there's a plentiful supply, lots of oxygen in the mixture, so complete combustion, carbon dioxide and water. If there's not enough oxygen, if there's an incomplete combustion is when there isn't a plentiful supply of oxygen, there's not enough oxygen, and in that case you would get carbon monoxide and water, or even carbon and water. But in this case we know there's complete combustion, plentiful supply of oxygen makes carbon dioxide and water. Let's balance it then. So we've done that already, but I can show you how it was done. C9, the only place where the carbons go, the carbon dioxide, so I need a 9 in front of the carbon dioxide to balance the carbons. H20, so I need 10 in front of the H2O because 10 times 2 is 20 to balance the H's, and now I balance the O's. 9 times 2 is 18, add 10 is 28, 14 times 2 is 28, so we need a 14 there. Non-N is often found in fuel for jet engines. Combustion in jet engines produces pollutants such as nitrogen monoxide. Explain how nitrogen monoxide is formed. Well, the nitrogen in the air reacts with the oxygen in the air. So nitrogen and oxygen react together, and the reason that happens is because there's very high temperatures in a jet engine. Non-N can be cracked to form large quantities of propane. Crack means you take long chains and you break them up into short chains. When you end up with compounds with double bonds in them, hydrocarbons with double bonds in their unsaturated ones, then the type of cracking used is called thermal cracking. Thermal, it means you're using heat to break the long chains down into shorter ones, and you get these double bonds. The other type of cracking is catalytic cracking, and you don't get double bonds in that. You tend to get cyclic structures. The main use of propene formed from cracking is to make polypropene. So what you do is you draw out polypropene with a carbon-to-carbon double bond and a carbon going up, and then you break the double bond and join them together. So the repeating unit, you can see what's happened here. There's been a carbon-to-carbon double bond, so it's been propene with a carbon-to-carbon double bond there, and then the carbon-to-carbon double bond there in the propene, 1, 2, 3 in propene. The carbon-to-carbon double bond is broken, and a bond has gone either side to make a really long polymer chain of polypropene. Question number 5. A hydrocarbon contains 87.8% biomass of carbon. Well, a hydrocarbon's got hydrogen and carbon in it only. So the only other thing in there can be hydrogen. So 12.2% must be hydrogen. So let's do spoilers and have a look what happens next. So when you've worked out the percentage of hydrogen by subtraction of 100, take away 87.8, then you divide by the molecular mass, the mass of each atom. So 87.8 divided by 12 and 12.2 divided by 1 gives you 7.3 to 12.2. We need these in whole numbers, so the next step is to divide by the smallest, that being 7.3. 7.3 divided by 7.3 is 1, 12.2 divided by 7.3 is 1.67. Now we need to multiply by a number to get this into a whole number. And that's a 3. So if you multiply this by a 3, it'll come out to be a 5. So multiply them both by a 3, 3 to 5. So the empirical formula is C3H5. However, if we add up the MR of each of these, a carbon's mass is 12, 3 12s and 5 1s for the hydrogens, it comes out as 41, and the MR is 82, it's double that. So it needs to be double this, so this empirical formula needs doubling to be its real true molecular formula, which is therefore C6H10. What could that be? Well, C6H10, an alkene is C6H12, an alkene, so take the number of n number of carbons and double it to 2n, but it's even less than that, so it probably means that it's got 2 double bonds in there, not just 1 double bond, but 2 double bonds. So things ways with 2 double bonds with 6, 1, 2, 3, 4, 5, 6. You'd have the double bond at carbon number 1, and then at carbon number 3. You could have the double bond at carbon number 1, and then at carbon 2, 3, 4. Or you could have the double bond at carbon number 1, and then carbon number 5. So you could have hex 1, 3 diene, hex 1, 4 diene, or hex 1, 5 diene. You could even have hex 2, 4 diene as well. So any combination where there's 2 double bonds in a chain of 6 would suffice. You could even have a cyclic compound of 6 with a double bond in there, cyclohexene. And then finally, name the type of reaction taking place when bromine water reacts with the hydrocarbon. So what actually happens is if bromine water Br2 would add across the double bond, the Br2 accepts the electrons from the double bond, so a curly arrow would go to one of the Brs, that will come off and attack a carbocation as a mechanism. So that's electrophilic, the Br, the Br2, the bromine is an electrophile and it adds across the double bond, electrophilic addition. Compound A is a halogenoalkane, so it's got a Cl group, it's got 5 carbons in a line, it's got 2 methyl groups, so it's pentane because it's got single bonds, 5 in a line. It's symmetrical, so it doesn't really matter whether we start labelling from the left or the right, we're going to end up with the same numbers for the methyl groups and the Cl, so it's 3-chloro, 2,4-dimethyl pentane. 3-chloro, carbon number 3, 2,4, number 2 and number 4, di-2-methyl groups pentane. It's important that you have the C for the chloro alphabetically before the M for the methyl. Let's have a look at this then now. Compound A has relative molecular mass of 134.5. The main isotope is hydrogen mass 1 and carbon mass 2. Chlorine consists of 2 common isotopes, 35Cl and 37Cl, of which 75% is 35Cl, so 3/4 of it, 3 parts out of 4, are 35Cl. 25% is therefore 37Cl. So this is 3 times more common. 35Cl is 3 times more common than 37Cl. The mass spectrum of A was recorded when A was ionized. So what actually happens is you have something called an electron gun. An electron gun removes an electron from this and makes it plus charge. Doesn't really change the mass because an electron has got negligible mass. So removing an electron doesn't really change its mass, but it makes it plus charge so that it can be accelerated down the mass spectrometer tube and then detected at the end. So basically it's saying that there are peaks for the molecular ions in the mass spectrum of A. What will they be? Well, if that's, you need to work out the MR. The MR with 35Cl I think will come out as 134, and with a 37Cl it'll come out as 136. So you're going to end up with peaks at 134 and 136. The one at 134 that's got the 35Cl, which is 3 times more common, will have a higher peak because relative abundance means how much of it there is. So if we had 1, 2, 3 lots, parts, amounts, whatever you want to call it, at 134, that would compare to 1 part at 136. A reaction with warm dilute aqueous sodium hydroxide. So if we're using dilute aqueous sodium hydroxide, then aqueous means water. So water, sodium hydroxide in water, what actually happens is you get nucleophilic substitution. So the mechanism is that this C to Cl bond is polar. So that's slightly electronegative. The Cl's electronegative gets a slight delta minus charge, slight delta plus charge, and the OH minus bonds with or attacks the C, because that's got a slight delta plus charge, and the Cl, which is withdrawing electrons because it's electronegative towards itself anyway, gets the electrons and forms a Cl minus ion. The Cl minus ion is missed off from this side, but it forms Cl minus. It's a minus because electrons are moved onto it, and the OH bonds where the Cl was. It can either be up or down, it doesn't really matter. In this case it's drawn going upwards. Important that you have OH minus and that you don't include the Na. The Na, the sodium, is a spectator ion. You only use the hydroxide part, which is OH minus, and it's important you show the lone pair because it's the lone pair that bonds to the C. That lone pair forms the share with a dative or a coordinate bond, a covalent bond between the O and the C. With hot ethanolic potassium hydroxide, so with hot, ethanolic means there's ethanol present. This time you don't get nucleophilic substitution. The OH minus doesn't attack that C. What it attacks is, if you go find the C with the Cl, there it is, there's the C with the Cl, and you go along another C. Either way, it doesn't matter in this case because it's completely symmetrical. You go along another C, from the C with the Cl, you go along another C, and you identify hydrogen bonded to that C, which is that hydrogen there. It's that one that it attacks. So the OH minus attacks that hydrogen there. So again, you identify it C to Cl, you find that carbon, you go along another carbon, either left or right, doesn't really matter in this case because it's symmetrical. Find the carbon, let's say to the left, and find a hydrogen bonded to that carbon. The OH minus bonds with it, and it actually makes water, HHO. So the H2O loses its minus charge because electrons are moving away from it, and it will make H2O. This bond then breaks and it moves in between the two carbons here, between the carbon that the H has been bonded to and the carbon with the Cl, and forms a double bond here, and then the Cl breaks off. So just like before in nucleophilic substitution, the Cl bond breaks off and it will make Cl minus as the electrons move onto the Cl. Mechanism, elimination. The reason it's elimination is because atoms have been removed from this. One product actually makes 3 products, Cl minus H2O, and this, which is got a double bond, an unsaturated hydrocarbon here. So atoms have been removed, eliminated, elimination, and the role of the hydroxide ions is the OH minus has gained an H plus to become water. So it's gained an H plus, something that gains an H plus. Remember, an H plus is an acid, and something that reacts with an acid is called a base. The infrared spectrum in figure 4 is that of either alcohol B or alkene. So we're looking for either an alcohol, an OH, or a double bond C. Which one is it? Well, it's easy to identify that actually it's not the alcohol. That's the easiest way of doing it, because an alcohol has a very, very broad absorption peak here, a really, really wide, deep absorption peak here. Not sharp like this, it's really, really wide. In an OH, either an OH of an alcohol or an OH of a carboxylic acid. The OH of the alcohol are both wide and broad. It's around about here, 3,000 to 3,500. It's around about here, 2,500 to 3,000 for the OH in a carboxylic acid. But in either way, as long as you've got an OH and an alcohol or a carboxylic acid, you end up with a really wide, broad peak here in its absence. So it's not alcohol, it's an alkene. A carbon-to-carbon double bond is actually that one there, around about 1,600, 1,700, something like that. It's not very big, it's hard to identify, and that's why it's easy to identify that it's not the alcohol, because it's not got the OH broad absorption at around about 3,000 to 3,500. Explanation. The carbon-to-carbon double bond, you must quote these numbers from your data book, 1,620 to 1,680. Remember, we're going right to left for our scale, so it is that one. So that one identifies the carbon-to-carbon double bond, or as I said, no OH at around about 3,230 to 3,550. Nothing here for an alcohol. Quote those numbers from your data book, you don't need to remember them. Compound D reacts with aqueous sodium hydroxide in a similar way to A to form alcohol B. Explain why D reacts more quickly than A with aqueous sodium hydroxide. Remember, dilute aqueous sodium hydroxide with water is nucleophilic substitution. So the OH minus is going to bond with, attack this carbon here or this carbon here, and the Cl breaks off, that bond breaks, and electrons move on to the Cl and make Cl minus. Or in this case, D, the only difference is instead of a Cl, you've got a Br breaking off, and that will form Br minus. Why D would react more quickly than A? It's simply because this bond between the C and the Br breaks more easily. It's weaker. So you can say the C to Cl here is stronger than the CBr, or the CBr is weaker than the C to Cl bond. 4 compounds, all colourless liquids, are butan-2-ol, butanal, butanone, and 2-methylpropan-2-ol. 2 of these compounds can be identified using different test tube reactions. It's the top 2 that can be identified with test tube reactions. Butanal is an aldehyde, so that can be tested with warm Tollens reagent. Put the word warm in as well, because at A2 you could need the word warm. Warm Tollens reagent, which will give a silver mirror, or if that wasn't available, then you could use Failing solution, which would give a brick red precipitate. Either of those 2 tests are fine. Butan-2-ol, so the OH is at carbon number 2 of 4 in a line, butan, so it's at carbon number 2. So either side of the carbon with the OH, you've got 2 carbons, a carbon to the left and a carbon to the right. It's a secondary alcohol. Now, a secondary alcohol will react with something like acidified potassium dichromate. Use the word acidified, it's got acid in there. Again, an important part of the test. Acidified potassium dichromate will go orange to green, and you need the orange to green, not just changes from orange or goes green, orange to green. So acidified potassium dichromate will go orange to green. Incidentally, it will form a ketone. If it had been a primary alcohol like butan-1-ol, it would have made an aldehyde, and then if you reflux it, carry on heating it, it would turn into a carboxylic acid. But either way, those are the 2 tests, and then you need a test for butanone. Butanone, well, there's no test, so you need a spectroscopic technique. In other words, you're going to use infrared spectroscopy and find the wavelengths, the wave number of the infrared light that's actually absorbed by the carbon to oxygen double bond as it vibrates or stretches. And again, for the 2-methylpropan-2-ol, you've got an OH group, and you've got to identify the wave numbers of those 2 absorption peaks. and you can find that from the data book. So methanol can be manufactured in a reversible reaction. Look, there's the sign for reversible reaction. It can go in the forward direction or the backward direction, as shown below. So what normally happens is you normally add the two reagents together and you don't end up with any product at the beginning, and at some point then dynamic equilibrium is reached. Dynamic equilibrium, sometimes just called equilibrium, but it should be called dynamic equilibrium, means that the concentrations of the reactants and the products no longer change. The concentrations no longer change of anything in the reactions or reactants or products, and the rate of the forward reaction, the rate of the backward reaction is equal, and at that point you've got dynamic equilibrium. State and explain the effect of using a catalyst on the yield of methanol. So what can actually happen is, depending on whether it's exothermic or endothermic, or depending on the number of moles of gas on the left or the number of moles of gas on the right, you can alter the position of equilibrium by raising or lowering the temperature or raising or lowering the pressure, using a principle to determine that, using called Le Chatelier's principle, which works to oppose the change that you've just imposed upon the system. Anyway, what effect does a catalyst have? And the answer is none. None whatsoever. It won't speed up the reaction to the right and make more of the methanol, and it won't speed up the reaction to the left and make more carbon monoxide and hydrogen, because it speeds up the forward and backward directions equally. So it doesn't make more of one of the products, so it doesn't make more of one of the reactants. It has no effect on the yield of methanol, the position of equilibrium. It doesn't shift the position of equilibrium to the right at all. What it does is it increases the speed of forward and backward reactions equally. It increases them both. Give an expression for the equilibrium constant Kc for this reaction. So it's the concentration of methanol on the right divided by the concentration of carbon monoxide on the left, and the concentration divided by the concentration of hydrogen. That's to the power 2 because it's got a 2 in front of it. The mixture of carbon monoxide and hydrogen is allowed to reach equilibrium in a container of 250 centimeters cubed at a temperature of T. So 250 centimeters cubed, divide by 1,000 to turn centimeters cubed into decimeter cubed, 0.025. At equilibrium, the mixture contained, so we've got the moles of each of them. So the first thing to do is, if you're going to work out Kc, you've got to turn moles into concentration. Concentration equals moles divided by volume, so concentration is moles divided by the volume. So I take the 0.340 carbon monoxide divided by 250 centimeters cubed in decimeter cubed is 0.25. 3.40 divided by 0.25 will give me the concentration of carbon monoxide. 1.90 divided by 0.25 will give me the concentration of hydrogen, and 0.051 divided by 0.25 will give me the concentration of methanol. And then I put those into the equation in the right place, and I work it out, and the answer will be 0.311. Sometimes you can get away without actually dividing by the volume, and you can just use moles instead of concentration. The way you know whether you can get away with that is because if you have equal numbers of moles on the left as you have on the right, then you can get away with it because you're dividing by the same number of volumes each time on the top and the bottom of the equation. But in this case we can't get away with it because we've got 1 mole of carbon monoxide and 2 moles of hydrogen. So we've got 3 moles on the left, 3 moles of reactants, and only 1 mole of product, methanol. So we need to use volume in this equation for this one. Methanol decomposes on heating, and it's the reverse. So what we've got is we've got the reverse equation. So instead of carbon monoxide and hydrogen making methanol, we've now got methanol making carbon monoxide and hydrogen. So in other words, everything is upside down. So if I did the Kc for this, it's the concentration of carbon monoxide on the top multiplied by the concentration of hydrogen on the top to the power 2. It's these two values now on the top, and this concentration of methanol on the bottom. So it's the reverse. So what you can actually do is you can just do 1 divided by this if you want to. I mean, you can put them all in again if you wanted to. You could have 1.36 times 0.76 squared on the top divided by 0.244 on the bottom. You can work it out again. Or if your maths is strong, you can realise that actually it's just the other way up. So instead of 0.311, it's 1 divided by 0.311. So whatever your answer is to here, 1 divided by that, or you can put all the numbers in again and it comes out as 3.22. What actually happens to these is, instead of the mole to the minus 2 dm to the 6, you actually reverse the signs now. So if it's upside down, it becomes mole squared dm to the minus 6. Question 9 and question 10 then. A student has 10 centimeters cubed sample of 1 times 10 to the minus 4 mole dm to the minus 3 methanoic acid solution. I'm not even going to read the rest of the question. I'm going to do this bit first because I know I've got to do this. I've got a volume and I've got a concentration. Why would they give me a volume and a concentration? Concentration equals moles divided by volume. Concentration equals moles divided by volume. So moles equals volume multiplied by concentration. So if I multiply these two together, I'm going to get the number of moles of methanoic acid. I'm not even going to read the rest of the question. I know I've got to do that, otherwise they wouldn't have given me a volume and a concentration. The one problem is, in concentration equals moles divided by volume, the volume's got to be in decimeter cubed. Taking a small unit value like centimeter cubed into a larger one like decimeter cubed, then I'm going to divide by 1,000, so that's 0.01. So 0.01 multiplied by 1 times 10 to the minus 2. Let's do spoilers. 0.01 equals number of moles divided 0.001, which is the concentration, equals moles divided by 0.01. So we've converted the centimeters cubed into decimeter cubed. So moles is these two multiplied together, as we said, which is 0.0001. Okay. Now then, so I know the number of moles of methanoic acid in my solution. Let's have a look now what's happening next. The student is asked to dilute the methanoic acid to a concentration. Right, we've got a new concentration. So the concentration has changed. We need to work out the new volume. So the concentration has just changed. However, all we've done is add water. We've not changed the amount of methanoic acid. There's no mention of adding more methanoic acid in there. The amount of methanoic acid, the number of moles of methanoic acid has stayed the same at 0.0001. So when diluted, the number of moles stays the same. So the new concentration equals moles divided by volume. New concentration, 2 times 10 to the minus 4 is 0.0002 equals the number of moles of methanoic acid stayed the same, 0.0001 divided by volume. Rearrange that and you'll find that volume is 0.0001 divided by 0.002, which is 0.5. Remember, the volume is in decimeter cubed. Now, all the answers, unfortunately, are in centimeter cubed. So let's convert decimeter cubed back into centimeter cubed. To turn a large unit value like decimeter cubed into centimeter cubed, you multiply by 1,000. So the volume equals that multiplied by 1,000, which is 500. I don't know why it says 250 centimeters cubed. That's wrong. 500 centimeter cubed, it should say. 0.5 decimeter cubed is 500 centimeter cubed. Now, what's it asking? Right, okay, it's not asking for 500 centimeter cubed. What is the final volume? Read the question carefully. So C is a red herring to try and catch you out. What volume of water should be added? So at the beginning, there's 10 centimeter cubed, and the final volume we know needs to be 500 centimeter cubed. So to turn 10 centimeter cubed into 500 centimeter cubed, you add 490 centimeters cubed extra of water. So the answer is B, with C as kind of red herring to try and catch you out. Which molecule does not have a permanent dipole? Well, a dipole means that you've got polar bonds overall. Now, all of them have got polar bonds. They've all got C to Br bonds. So each of those are polar with a delta plus and delta minus. But something wouldn't have a permanent dipole, i.e. A permanent dipole means that the delta plus and delta minus, the polar bonds, don't cancel each other out. So something that does not have a permanent dipole means that the delta plus and delta minuses around the molecule all cancel each other out. That happens if it's perfectly symmetrical. So if in 4 positions, up, down and left and right, you have the same group. So the answer is D, because it's got CBr4. So it's got a polar bond to the top, to the bottom, to the left and the right, and it's perfectly symmetrical. And so all the delta plus and delta minuses all cancel each other out. So you don't have a permanent dipole. It's not got a dipole, a delta plus or a delta minus in one direction. Questions 11 and 12. Both are quite tricky actually, especially question 11. So what have you got? What's the major product of the reaction between 2-methyl-butene iodine monochloride? So 2-methyl-butene. So before this has reacted, it's had a double bond between carbon numbers 2 and carbon number 3. So this is carbon number 2, 2-methyl, there's the methyl group, butene, so it's had a double bond here. So the I and the Cl have bonded across the double bond. Now they're in the wrong position. They need to bond across this double bond at carbon number 2. They're in the wrong position. C are in the right position and D are in the right position, across in between carbons number 2 and number 3 where the double bond has been. So ICl has bonded across that double bond. So A and B are automatically incorrect. The question is, which way round are these two? Well, if you imagine, if you had HBr, let's say, H is HBr, the Br is slightly electronegative, so it gets a delta minus, and the H has got a delta plus. And the H bonds on first because it's got the delta plus. So the double bond would attack the H plus of HBr, and the H bonds on to the carbon that's got the most hydrogens. So the H would bond on here, and then the Br would bond on there. So now, instead of HBr, you've got ICl. So which way round is the delta plus and delta minus on ICl? Well, Cl is more electronegative than I because it's a smaller atom and withdraws electrons closer into its nucleus more readily, so more strongly. So it will be delta plus on the I and delta minus on the Cl. Let's just show you that. So it's delta plus on the I and delta minus on the Cl, just like I had HBr, with Br being more electronegative than the H and ended up with a delta minus on the Br and a delta plus on the H. That's the way this goes because Cl is a smaller atom than I and would end up with the delta minus across this polar bond. So in other words, ICl is similar to HBr, and if the I were an H of HBr, you know that it would attack, join on across the double bond onto the C of the H there, because that C has got an H, this C has got no H's, and the H of HBr would bond onto the carbon that's already got the most H's. So the I is similar to the H and would bond onto there, and then the Cl would bond onto this one. So the answer is C and not the other way around. If you want to know the understanding of why a H of a Br or an I of a Cl would bond onto the carbon with the most number of H's, it's because when it bonds on, that C doesn't have the Cl bonded to it yet. It would have a plus, and that would be a tertiary carbocation, a C with a plus with 3 other carbons around it, making it stable because the methyl groups repel electrons. So that is why it happens. But it's not asking why it happens. You just need to imagine that ICl is similar to HBr, and then you can work it out knowing that the H, or in this case the I, bonds to the carbon which has the most hydrogens, and that is the position of the double bond at carbon number 2. So that is why these two are incorrect. They're bonding across between carbons number 1 and number 2 and not between 2 and 3. Which statement is not correct about the industrial preparation of ethanol by the hydration of ethene? So the reaction is catalyzed by an acid. Not sure. So we'll leave that one for now. A low equilibrium yield of ethanol is acceptable because unreacted ethene is recycled. Not really sure. A and D could be plausible, but if we're not sure, let's have a look at B and C. Let's work out the others. The higher the pressure, the higher the equilibrium yield of ethanol. Well, I've got 2 moles of gas on the left, 1 mole of this and 1 mole of this, and I've only got 1 mole on the right, so I've got 2 moles of gas on the left and 1 on the right. So a higher pressure, by Le Chatelier's principle, if I increase the pressure, it will try and lower the pressure. It will lower the pressure by reducing the volume and making 2 moles of gas into 1. So yes, increasing the pressure would increase the amount of ethanol by shifting the position of equilibrium to the right. So that is definitely right. A and D we're not sure of. Let's check out D. If that's the one that's not correct, we know we've found it. The higher the temperature, the higher equilibrium yield of ethanol. So in other words, does increasing the temperature make more ethanol? Does it shift it to the right hand side? That's what the question's asking. Well, it's got a minus here, so it's exothermic. So that means that when this reaction happens, it gives out heat. If I increase the temperature, higher the temperature, by Le Chatelier's principle, this reaction will respond to try and lower the temperature of the system, lower the temperature of the surroundings, and oppose the change. That's what Le Chatelier's principle says. So if I increase the temperature, it will try to lower the temperature of the surroundings. Well, it's not going to go to the right and make more heat. It would shift to the left to reduce the amount of heat. So that increase in the temperature wouldn't increase the equilibrium yield of ethanol. It would actually increase the equilibrium yield of ethene and water or steam by shifting the equilibrium to the left, reducing the amount of heat in this direction, which is endothermic. Question 13, 14 and 15. Which compound has the highest boiling point? So what you're looking for is you're looking for the strongest intermolecular bonds. The strongest intermolecular bonds are hydrogen bonds. It's where within one of these molecules you've got a hydrogen bonded to an oxygen, a nitrogen or a fluorine. And the bond between the hydrogen and the oxygen, the nitrogen, hydrogen, the oxygen, or the hydrogen, the nitrogen, or the hydrogen, the fluorine is very polar. So you get large delta plus and delta minuses set up, and then that attraction between those polar bonds and a neighbouring molecule is called a hydrogen bond. It's just basically a very, very strong dipole-dipole attraction. The next next highest boiling point is that where you've got polar bonds. So say for example a carbon bonded to an oxygen, or a carbon bonded to a Cl, or a carbon bonded to a Br, or a carbon bonded to a fluorine. So you've got a polar bond there. It's not as strong, it's not as polar as a H bonded to an O, or a H bonded to an N, or a H bonded to an F. That's really polar and got large delta plus and delta minuses, but it is polar if you've got a C bonded to a Cl, an F, a Br, an I, or an O. And that would have the next highest boiling point, and the kind of intermolecular bonds between those kind of molecules are called dipole-dipole attractions. And then if you haven't got any polar bonds within the molecules, you've got van der Waals forces, the force of attraction between the electrons in one molecule and the nuclei, the positive nuclei in the neighbouring molecule, and that's the weakest form of intermolecular bond, and that would have the lowest boiling point. So first of all, I'm looking for highest boiling point. I'm immediately looking for a molecule with a hydrogen bonded to an oxygen, a hydrogen bonded to a nitrogen, or a hydrogen bonded to a fluorine, because that's going to be really polar. And then if that's really polar with large delta plus delta minuses, you get a really strong dipole-dipole attraction to the neighbouring molecule called a hydrogen bond. Butanal, let's go through these then. Butanal has got a carbon to oxygen double bond, so it's polar. You've got delta plus and delta minuses. On the neighbouring molecule you'll have a polar bond, and you have dipole-dipole attractions, but it's not a hydrogen bonded to an oxygen, or a hydrogen bonded to a nitrogen, or a hydrogen bonded to a fluorine. So the polar bond between the carbon and the oxygen is not as polar as it would be if you had an H to an F, an H to an O, or an H to an N. So medium boiling point. Yeah. Butanol, here we go, we've got an OH in there, you've got an oxygen bonded to a hydrogen, so that's going to be very, very polar, that bond, and so an O to an H is going to have a large delta plus on the H and a large delta minus on the O. Very, very polar bond, very, very strong intermolecular bonds, hydrogen bonding. B is going to have the highest boiling point probably. Of all of these, but let's go through them. Butene is a hydrocarbon, no polar bonds, so intermolecular van der Waals forces between those. Now this is a tricky one because it's got a fluorine in there, an F, but it hasn't got an F bonded to an H. It's got an F bonded to a carbon, so the F bonded to the carbon in one fluorobutane is going to be a polar bond, and therefore you'll have dipole-dipole between them. So dipole-dipole, dipole-dipole, medium boiling points, low boiling points for this one with no polar bonds and van der Waals. This one's got hydrogen bonds because it's got an oxygen bonded to a hydrogen. Your answer is B. Which statement is correct about the fractional distillation of crude oil? Tricky question this. Zeolite catalyst. No, that's used for catalytic cracking, the breaking of long chains into short chains using a catalyst. Each fraction contains a mixture of hydrocarbons. Well, that's true. You might think when you do fractional distillation of crude oil, each fraction, each set of liquids is pure. It's not. It's still going to have a mixture because you're never going to get complete evaporation at any one particular boiling point. You're heating it up and you've got different boiling points within the flask, so different temperatures within the flask, so things will boil at different temperatures, even within the flask, because you never get one precise temperature. And again, in the fractionating column, it's hottest at the bottom and coolest at the top. So you've got temperature gradients in the flask and the fractionating column, so you haven't got one precise temperature. So you're going to get a mixture of hydrocarbons boiling, even though as best you might try, you're trying to get pure fractions coming off. They're never going to be pure. So B is your correct answer. Gaseous fractions are formed by breaking covalent bonds. No, you don't break covalent bonds. You're not breaking covalent bonds within molecules. When you're actually heating something up and making gases out of liquids, when you're evaporating these during distillation or fractional distillation, you're breaking intermolecular bonds, bonds between molecules, not the covalent bonds within the molecules. The fractionating column is hottest at the top. No, it's hottest at the bottom because you're heating the flask up at the bottom. That's where your heat's been provided from the bottom. So it's hottest at the bottom and then coolest towards the top. How many structural isomers with an unbranched chain have a molecular formula C4H6Br2? So I'm going to do spoilers here. So where can the BRs be? They can both be at carbon number 1, both be at carbon number 2, 1 at 1 and 1 at 2, 1 at 1 and 1 at 3, 1 at 2 and 1 at 3, and 1 at 1 and 1 at 4. And those are all your combinations, and that's why it's 6, answer C. Questions 16 and 17. So I've got a Maxwell distribution curve here. Right, along the bottom you've got energy, and up the side you've got numbers of molecules. So first of all, which letter represents the mean energy? Energy is along the bottom. So you're looking at either C or D as a value for energy along the x-axis. A and B would be the number of particles. So immediately you're down to C or D. Now the question is, at the height of the peak here, this is the energy. C is the energy that most particles have. These number of particles going up the side, you can see most particles at the peak. A is the most number of particles at energy C. So A is the number of particles of the energy that most particles have. That's number of particles. C is the energy that most particles have. Offset to the right, so to the right hand side, right of the peak, this D is the mean energy, the average energy. It's not the most energy that particles have, the energy that most particles have, it's the mean energy, and that's D. And B therefore is the number of particles with the mean energy. So the mean energy is offset to the right of the peak. Ethanol can be made by glucose for fermentation. I've been given a mass and an MR of each, so I need to work out number of moles of each. Moles is mass divided by MR. So for moles of glucose is mass divided by MR. Mass of glucose, I need to convert kilograms into grams first of all, though, however, because mass is in grams. So kilograms, a large unit value, into a small unit value, and multiply them by 1,000. So 1.44 times 1,000 is 1440. 1440 divided by the MR, I've got 8 moles of glucose. Ethanol, numbers of moles, well, I've got that in grams, so that's easy. 268 divided by 46, I've got 5.83 moles of ethanol. Now, if I look in the equation, 1 mole of glucose should make 2 moles of ethanol. So if I've started off with 8 moles of glucose, 1 mole makes 2, 8 moles should make 16. I should be making 16 moles of ethanol, but I've only made 5.83 moles of ethanol out of the 16 that I theoretically could have made. So 5.83 is what I did make, moles. 16 moles is what I theoretically could have made. And so I'll divide the smaller by the larger, times by 1,000, 36.4, and my answer is B. Questions 18, 19 and 20. Some tricky questions here. 18. Which could act as a nucleophile? So what's a nucleophile? That means plus loving translated from Greek. But actually what it means, what its definition is, plus loving, nucleophile translated. Its definition, what it actually is a lone pair donor. So it donates its lone pair and attacks bonds with atoms that have got a plus on them. It's plus loving, but it's a lone pair donor. So we're looking for something with a lone pair. Let's have a look. BH3. Now, B, boron, is in group 3. It's got 3 electrons in its outer shell, and it's got 3 bonds to the H's. Those 3 electrons in the outer shell are all bonded up. They're all in bonding pairs with the H's, so that hasn't got any spare lone pairs. NH4 plus. N is in group 5. It's got 5 electrons in its outer shell. However, it's got a plus. It's lost an electron. So it's now got 4 electrons in its outer shell, and they're all bonded up in bonding pairs to 4 H's. So that's got no lone pair of electrons. It's got no spare electrons. pH3, here we go. P is in group 5. 5 electrons in its outer shell, 3 of them in bonding pairs, but there's 2 left over. There's a lone pair, a pair of electrons on that P that are not involved in bonding. SiH4, silicon is in group 4, 4 electrons in the outer shell, all involved in bonding pairs with the 4 H's. Your answer is C. Which statement is true about polychloroethene? So polychloroethene has come from a chloroethene, in other words, a C to C double bond with HHHCl. So it's C to C double bond, an H and H on carbon number 1, and an H and a Cl on carbon number 2. And when it's formed polychloroethane, the double bond is broken, and then all of the monomers are now joined together with single bonds. So let's have a look. The empirical formula is CHCl. No, I've said I've got C to C and I've got HHHCl. So I've got 2 C's and 3 H's and a Cl. I've not got equal numbers of each. So that's not true. It decolorizes bromine water. In other words, turns bromine water from orange to colourless. No, it's not going to do that unless it's got double bonds. And in polychloroethene, the double bonds are broken to make single bonds in a very long chain. It won't decolorize bromine water. It's got single bonds. Its brittleness is reduced. In other words, brittleness reduced. Brittle means it's going to snap. Its snap is reduced. So it's stopped being stopped snapping with plasticizers. That's true. Plasticizers soften a polymer. They're used to soften a polymer. Something like, let's say, for example, the insulation around wires is soft plastic. Plasticizers are also used in rubber, so for rubber tires to make it softer. That's true. So it's made flexible by using plasticizers. The polymer chain contains alternate single and double bonds. Now the double bonds are broken to make single bonds. Your answer is C. What is the enthalpy of formation of buta-1,3-diene? So I'm going to do spoilers here and show you actually doing hand drawn here what's actually happening. So formation is when 1 mole of substance is made from their elements in their standard states. That's important to know. Enthalpy of formation. So formation means that you're making this buta-1,3-diene C4H6 from elements in their standard state. So it's formation of 1 mole of this. I've got 1 mole of C4H6. That's important. 1 mole of this from elements in their standard states as you'd normally find them in the laboratory at room temperature. So you'd normally find carbon as a black solid, like in the inside of pencils. Hydrogen is gas, H2. And so balancing it, C4, I'll need 4 C's because carbon is a C. A black solid, 4 of those, and I'll need 3 H2s. That makes 6 H's to go in there. So now I need to know the enthalpy change of this, but I'm not given it, but I've got the enthalpy change of some other reactions. So I can look at the alternate route and add these together, a process called Hess's law, to add these together to work out what this would be from my other reactions, my alternate routes. So let's have a look. What have I been given? I've been given the enthalpy of combustion of carbon. So enthalpy of combustion. Combustion means a reaction with oxygen. So I've reacted the carbon with oxygen to make carbon dioxide. If it's complete combustion, I've got plenty, full supply of oxygen. So I've added oxygen and made carbon dioxide. 4 carbons would make 4 lots of carbon dioxide. Okay, we'll work out what the enthalpy change for this is in a minute. I've got 3 H2. H2 would burn in oxygen, combust in oxygen to make water, a process that happens when rockets are fueled. So H2 would make H2O, and I've got 3 H2, so I've got 3 H2O. So I've got 3 of these reacting. C4H6 would make 4 carbon dioxide and 3 water. It would just react with oxygen and make carbon dioxide and water. As long as there's a plentiful supply of oxygen, I get complete combustion to carbon dioxide and water. So I've got these 3 reactions going on. Let's work out the enthalpy changes. So I've got the enthalpy change for 1 carbon being combusted. I need 4 carbons combusted, so I'll multiply this by 4, minus 1576. It's still got a minus sign because it's going in the right direction, carbon making carbon dioxide. 3 lots of hydrogen going to water. Hydrogen combusting, 1 mole of hydrogen combusting is minus 285, but I've got 3 of them, so that's 3 times minus 286, minus 286 is minus 804, going in the right direction, still going in this direction, hydrogen being combusted to water, so it still retains its minus, it's still going to be exothermic, highly exothermic, as a rocket being fueled is. This way I've got C4H6 going to form my carbon dioxide and water, and so I've got minus 2546, and there's only 1 mole of this, because 1 mole of substances formed by elements in their standard states as part of formation. So I've got 1 mole of this, so I don't need to multiply it by anything other than 1. However, if I'm looking at this reaction here, carbon and hydrogen forming this C4H6, I'm going in this direction. These need to reflect this. I've got to come round in this direction. Now they're in the right direction, so they keep their minus signs. However, this one, this combustion, is coming this way, and I need it to go from here to here to here to here to here. I need to reverse this sign. It's in the wrong direction, and so what I'll do to reverse the sign is that a minus becomes a plus. So it's the same enthalpy change, except that instead of giving out heat this way it will take in heat, and instead of being exothermic with a minus, it becomes a plus. So now I've got plus 2546. If I add together minus 1576 minus 804 and plus 2546, I end up with answer A, which is plus 112. Question 21, 22 and 23. A gas cylinder contains 5 kilograms of propane. So I've got a mass and I've got the name of a hydrocarbon. I could work out its molecular form, I could work out its MR, I could work out moles from that if I wanted to, from mass. Moles is mass over MR. Where's it going to take me? Propane, a number of particles in a mole. Yeah, so I need to work out the number of moles. So first of all, let's do spoilers. Moles equals mass divided by MR. The problem is that the mass is in grams. I need the mass in grams, and I've got it in kilograms. Kilograms down to grams, so down to a smaller unit, you're going to multiply by 1,000 from a large unit like kilograms down to a smaller unit like grams. 5 times 1,000 is 5,000. The MR of propane, let's just check that, is C3H8. 3 carbons at 12, mass 12 each is 36. 8 hydrogens at mass 1 each is 8. 36 add 8 is 44. So 5,000 grams divided by an MR of 44, 113.63. This is the number of particles. Avogadro's constant, 6.022 times 10 to the power 23. That's the number of particles in 1 mole. You never need to remember that number, it's always given to you. But it's the number of particles in 1 mole. Now I've got an awful lot more than 1 mole. I've got 113.63 moles. So if that's the number of particles in 1 mole, if I multiply by 113.63, I'll end up with the number of particles in this sample of 113.63 moles. 6.8 times 10 to the power 25, my answer is C. Which sample of liquid has the greatest volume? So what I've been given, density. Now that's a giveaway because density is mass over volume, and I've been given masses as well, so I'm going to use density as mass over volume to work out volume. Now we'll do spoilers again so we can see this. Density is mass over volume. I can rearrange that using triangular method or whichever mathematical method you use to rearrange equations. So volume is mass divided by density. The one problem is if I look at these units of density, it's grams per centimetre cubed. So my mass needs to be in grams, not milligrams, it's sometimes given, grams, and then I'm going to get my answer in centimetre cubed for all of them. That's fine. 500 milligrams. Milligrams, a small unit into a larger unit, are going to divide by 1,000. So a milligram, 500 milligrams divided by 1,000 is 0.5 grams. Density 0.63, 0.5 divided by 0.63, 0.79. So my volume in centimetre cubed is 0.79. B, milligrams again, divide by 1,000, 0.65, divide by its density, 0.8, 0.81 centimetre cubed. This time I'm giving it in grams, so this is easy. 1.20 divided by 1.33, 0.9. Again, grams, 1.3 I've got the right units divided by 1.48, 0.88. My highest value is 0.9 centimeters cubed. The answer is C. Which equation represents the initiation step? So I've got free radical reactions. Now this looks quite complicated, but it's really not. An initiation step is where something like chlorine, Cl2, with UV light forms two chlorine radicals. So you've got a molecule with two atoms joined together, or a number of atoms joined together, and the bond breaks, and one electron goes one way and one electron goes the other way. So the pair of electrons, the electrons separate, one electron go one way and one electron go the other way. And the way that you show that pair of electrons has become unpaired, and unpaired electrons is a dot. So you're going to end up with two species with a dot. So in other words, you can have no dots on the left because the bond hasn't broken, initiation step. The UV light will then break it and make two species with a dot. Well, here on the left I've got a dot. I don't want a dot on the left. I want no dots on the left. I want two species with dots on the right. I've got a dot on the left, not correct. I've got a dot on the left, not correct. And I haven't got two dots on the right of either of A, B or C, so the answer must be D. No dots on the left because no bonds have been broken, and then one of the bonds has been broken and one of the atoms has got one electron back, an unbonded electron, and the other atom's got an unbonded electron, and I've got two dots on the right. So for initiation step, no dots on the left, two dots on the right, the answer is D.